Okay, so I'll just get started.
Yep.
Okay, all right. Nice to meet everybody. I'm going to give my talk today on the title is Coordinating Decisions via Quantum Telepathy. So this was joint work with Liang Jiang at University of Chicago, and this is a paper that we put up on the archive middle of last year. Okay. So I'll start with a quick introduction. So first, a little forward. I would say that my own opinion and maybe opinion of a lot of people in the field is that one of the most critical questions in our field of quantum information science at our current stage is the following. What are good applications of quantum technology? And what I mean by good there's several different criteria for what I mean by good here. One is that I would like the application to have provable or a strong case for a quantum advantage. Like we really have an advantage for using this quantum technology over all possible classical technologies. And usually, at least for quantum computing, to have this kind of provability or strong case for an advantage, you make some complexity theoretic assumptions. For example, BQP is not equal to BPP, random circuit sampling is hard, factoring is hard. Those are kind of things that you need to say you have a quantum advantage. That's nice. That's okay for most part, but it'd be good to find maybe other examples where maybe you don't need that. Another criterion is that we have hardware right now. We have NISQ hardware. It's noisy. We don't have that many qubits. We're not doing fault tolerant operations or quantum error correction at a large scale yet. We really want to answer the question of what can we do with this hardware. And a good criterion for a good application is that this application only needs this kind of near-term NISQ hardware that we already have or we can have in the near future. And one of the answers that we're trying to propose to this question of what is a good application for quantum technology is what we call quantum telepathy. So quantum telepathy is kind of a controversial word here. It's related to the term that's already in the literature called pseudo-telepathy from a paper from 2003. It is basically the meaning of quantum telepathy. This means Bell inequality violation, so nothing very fancy, something we're all very familiar with from the fundamentals of quantum mechanics. And from another computer science or theoretical computer science point of view, it's also known as a quantum advantage in non-local games. So usually when we think of Bell inequalities, we think of this as something about fundamental physics or philosophy, like something really weird about entanglement or something that's like challenges our fundamental understanding of reality. It's kind of like at that level of our understanding. But what I want to argue in my talk here and the paper that we put on archive is that quantum telepathy is actually something that can be made into a technology, something that can have real world applications. And to kind of facilitate that kind of understanding, we had this patent back in 2020 with some colleagues at Alibaba, where I interned at. And we came up with this framework called the tacit coordination, or what we call a TC problem framework. And what this means is it's a little different from the current framework for Bell inequalities or non-local games. But it's pretty much the same idea. It's basically some kind of description of a Bell scenario or a non-local game. And a TC problem, tacit coordination problem, is basically an instance where you have some kind of coordination task where there's multiple non-communicating parties that are making local observations and decisions. They're seeing something in their local area, and they're making decisions in their local area, and they're not able to communicate. And you can kind of think of this kind of abstractly by using this diagram here. There's two bubbles showing the two different parties, 1 and 2. They're each seeing some observation, local observation, O1, and then some local observation, O2. And they are trying to make their own local decisions, D1 and D2, all without communication. And in this coordination task, what they're trying to do in the end is they're trying to maximize what's called a global utility. some kind of utility of collective decisions based on your collective observations. So given what you've seen, you make some decisions and you want to maximize that utility. And utility you can kind of think of as this kind of matrix here. So you can see the different observations that each party is making, like O and O prime, and decisions D and D prime. And so that for each like possible set of observations, O, like for example, the first row, they both see some observation O. Then if they make the same decision D, then they achieve a utility of U11. So it's basically a matrix telling you that given your observations, what is the utility of the set of decisions that you have made. So a TC problem is kind of abstract from what I explained from before, but it actually can appear in real life scenarios. And one example that we want to highlight is in high frequency trading, or I call what is simplified as HFT. So an HFT, I would argue, is a very natural instance of a TC problem. It's actually pointed out in a paper in 2016, also in our patent in 2020. It's very simple. So basically in high frequency trading, you're making these kind of trading decisions at very high speeds, very short time scales. What people are usually doing is they have these what we call co-located servers. So here's a picture here, for example, of two different exchanges, NYSE and NASDAQ. And in high frequency trading, they have these servers that are co-located. They're physically at the exchange, physically at NYSE or physically at NASDAQ. And what they're trying to do is they're looking at some local observations, some maybe like stock price fluctuations or other information that they can see at NYSE or at NASDAQ. And then they make some local decisions. They buy or sell stock or do some other kind of operation. And sometimes you can imagine scenarios where maybe they're trading like correlated stock or like associated instruments where they have to make a globally optimal pair of trades given their pair of observations. So this really matters what they're doing together as a coordinated group. And here in high frequency trading, because they're making these decisions at very short time scales, they cannot communicate with each other during this kind of operation because of latency. So in high frequency trading, it is well known that they are making these trades at like sub-microseconds or like 100 nanosecond kind of time scales. And that's like the fastest that people can go right now. But just given the physical distance between different exchanges, as you can see in this picture, that NYSE and NASDAQ, they're around 50 kilometers apart. So they're around the even speed of light in vacuum. The latency is about 200 microseconds. So if you're making sub-microsecond timescale decisions, you cannot communicate because of latency. It's that simple. And with the setup, the basic idea is you have this high frequency trading HFT scenario. You take that scenario, you write down the TC problem, like what is the decisions, observations that you can make, and what is the possible utilities of each possible decision operation pairs, the decision observation pairs. And then after you define that TC problem, you just find a quantum strategy with a higher utility than all possible classical strategies. And this is basically equivalent to violating a Bell inequality. And what I'm saying here is that when you violate this Bell inequality, that translates into a higher payoff or some other benefit, better kind of trading strategy that results from your experiment. Okay, so this is the basic idea. And what I want to highlight is that this is actually a really good application as what I described before. The first criterion, like we can prove that Bell inequality violation provides a quantum advantage. This is a very simple mathematical proof. There's really, it's very straightforward. There's not really any strings or conditions necessary here. And in fact, people take this this kind of phenomenon as a very strong indicator of an advantage, a quantum advantage. So it's actually used to prove a quantum advantage in other settings. For example, for shallow quantum circuits, that paper by Prof, Gossett, and Koenig in 2018, they used Bell inequality violation to prove that shallow quantum circuits have a quantum advantage. So for Bell inequality violations, there's not even any complexity theoretic assumptions. You don't need to assume BQP is not equal to BPP or something like that to establish that you have made a quantum advantage. And even breaking RSA, you would say is a quantum advantage using a quantum algorithm like Shor's algorithm, assuming factoring is not in BPP. So you still have to make that complexity theoretic assumption. But for Bell inequality violations, you do not need to make that assumption. And the second criterion is that we can actually realize this with NISQ hardware. In fact, you can actually realize this 50 years ago. This is the Nobel Prize back in 2022. These series of experiments in the 70s and 80s are already able to achieve these Bell inequality violations. And I want to point out that even for these kinds of applications, it's very demanding, like hardware requirements such as fault tolerance, a huge overhead of qubits, is really not strictly necessary to get a quantum advantage. So for example, violating the CHSH inequality, you require 2 physical qubits and just single qubit operations. So there's really not much you need on the hardware. Of course, you need these kinds of photonic connections, and that's an experimental challenge in itself, but we're already able to address that with current technologies, or even back in the 70s. Okay, so this is a quick outline of my talk. So if you just want to take just one thing away from this talk, it's basically this. Bell inequalities or non-local games actually appear very often in the real world, and provable quantum advantages can be attained with currently available or near future technologies. So the core insight from behind this is that the speed of light delay is actually pretty long compared to the timescales of modern classical processor operations. So it's actually very common to not be able to communicate between different parties, even at very short distance scales. So what I mean by short distance scales is something that can be achieved with entanglement distribution technologies. So I'll start with some definition of TC problems. And then second, I will go into a very detailed example of a HFT scenario that leads to a quantum advantage. It's called the hedging problem. And then thirdly, I will talk about how do you physically implement these quantum telepathy schemes. And then fourth, I'll end up with a discussion. Okay, so we'll get started. First thing I'll be talking about is the definitions that you need for TC problems. So a TC problem is what I described before. I'll go into more details of what I mentioned before. First of all, you name multiple parties that are making some coordination. They are engaged in some kind of coordination task. Each party makes an observation, O. So O is like the vector O. It's basically the observation of each party combined together into a vector. And then each party also makes a decision D. I'll call that vector D. That has all the decisions of each party combined together into a vector. And in the end, the goal of the TC problem is to maximize a global utility. So utility, you can think of it as for some reason, it's not in the same order. But the utility, you can think of this as a matrix, as I mentioned before. Given your observations, and you make these possible decisions, what is the utility that you achieve with that combination? And then the last thing that you need to define your TC problem is what I call the input distribution. So you have different observations that each party can make. There's a distribution of what observations can appear, and that should be also part of your TC problem specification. And then given these together, this utility array, this input distributions, possible observation decisions, those things together completely define the coordination task that we want to achieve. Hello? Okay. I'll just keep going. All right, so all right, so I'm talking about the strategies and behaviors. So we now have this specification of a TC problem, different observations, decisions, utilities. Before they actually start engaging in this TC problem or solving this TC problem, the parties prepare a strategy to solve the TC problem. So basically, what we're assuming here is that before they start, for example, in high-frequency trading, before they start trading, they already have an idea of what the utility array and the input distribution are like. So you can kind of think of as they do some kind of market research. They figure out, okay, if I see this and this, if I see this at NASDAQ, if I see this at NYSE, and I make these trades, then I make X money. You can kind of guess what will happen given some market history data. So this is already given in advance. And given this, the TC problem specification in advance, you want to decide on a strategy to maximize your utilities. And then when you implement this strategy, it leads to what we call behavior. So behavior is very simple. It's basically a conditional probability distribution. So basically, given your set of observations, vector O, what is the probability that you make a set of decisions, vector D? So this is basically also like a 4x4. You can write as a 4x4 matrix. For each row is going to be like a probability vector. So given, for example, the first row, if both parties sees observation O, then they make these 4 possible sets of decisions with each of different probabilities, P11, P12, P13, and P14. So this is what we call a behavior. And then when you implement a behavior, you want to choose that strategy so that your behavior maximizes your expected utility. So expected utility is basically you have all these probabilities going on, probabilities of different observations, probabilities of different decisions, and then you just average that over the utility values. So you can see here, you're making the, are you able to see my mouse, by the way? Hello?
Yes, I can see it.
Okay, all right. So for example, you're just making an averaging between observations and decisions, POO, POD, this together gives you a distribution over observations and decisions, and multiply it by the corresponding utility of that observation and decision combination, and that you average that and you get your expected utility. So you have to choose a strategy such that your POD gives you the largest possible U bar to solve your TC problem. Okay. So we'll start with the most straightforward strategy called deterministic strategies. So the most straightforward strategy, if you can't communicate, you're trying to do something with different parties, the most easy thing you can do is you just make a decision based on your own local observation. So this strategy is specified by functions F1, F2, which take O and O prime, the 2 possible observations that you can make, and then spits out a decision D or D prime. So F1 is the function that party 1 uses, F2 is a function that party 2 uses. These two together specifies a deterministic strategy. So the more general thing that you can do, what we call classical strategies, is you can do something a bit more where you can employ shared randomness. So you can like flip a coin, you use F1 if it's heads, F1 prime if it's tails. You can also like share coins. You flip a coin, make a copy, you give it to different parties, and then you can kind of realize shared randomness using that kind of strategy. So classical strategies is basically or also known as hidden variable theories, is what John Bell proved or said in the 1960s paper that is the most that classical mechanics can do. So classical mechanics is a special case of a hidden variable theory. So the best thing they can do for a TC problem is to achieve a utility that's achievable by a classical strategy. So you can imagine if they are just classical strategies, they're just doing shared randomness, some kind of random combination of deterministic strategies. In the end, their behavior is going to be a convex combination of deterministic behavior, some probabilistic combination of deterministic behaviors. You can imagine that's how it works mathematically. So by linearity, as you can see in the previous equation, that expected utility is linear in your behavior. So your expected utility for a classical strategy is also therefore a convex combination of deterministic strategies. And so if you want to, in the end, you just want to maximize your expected utility, it is actually just sufficient to only consider deterministic strategies, because for classical strategies, it's just going to be a probabilistic combination of those of deterministic strategies. Okay, so that's the that's what was the best you can do for classical strategies, and we call the maximum utility that you can achieve the classical value, or C star. Okay, and then I'll go on to quantum strategies. So for quantum strategies, it's basically the same setup as Bell inequality violation experiments. What they do is you first share some entangled particles beforehand, like psi AB, between the two parties. And then what each party does is they choose a measurement let's say, projective measurement based on your observation O. So for example, some party 1, they see some observation little o, and then they implement a projective measurement pi I indexed by O. So for example, if they see observation O, they do an X measurement. If they see observation O prime, they do a Z measurement. So the measurement is based on your observation. And after you make your measurement, you get a measurement result, and you use the measurement result for your decision. So what you do with this kind of strategy, this quantum strategy, it leads to a final behavior that looks like this. So remember, a behavior is a conditional probability distribution. So given your observations O1 and O2, observations O1 and O2, what is the probability of making decisions D1 and D2? And that is given by this equation. So if you see O1 and O2, so for example, party 1 sees observation O1, then they do they use a projective measurement pi indexed by O1. And then the probability of them doing D1 is given by the projector corresponding to D1. And similarly for party 2. So they see observation O2, and then you look at the projector corresponding to decision 2. And then you sandwich this tensor product of projectors by the shared entangled state. So basic quantum mechanics, this is this probability that you make decisions D1, D2, given observations O1 and O2. And then what I want to emphasize here is that in this whole process, there is no communication between the two parties. All they're doing is they have this shared entangled particle that they just have beforehand, and then they just see some observation, they make a measurement, like they change their measurement setting, and then they do a measurement, and then they do make a decision. So there's no communication at all. And this is why you can implement this strategy faster than speed of light latency. And that's what you need to get a quantum advantage. And if you maximize this, for example, this expected utility over all possible quantum strategies, then you get this what we call the quantum value, or what I denote as Q star. And then in the following slides, I'm going to be talking about quantum advantage. What that means mathematically is basically the difference between Q star and C star. And you can kind of convince yourself that quantum strategies is a superset of classical strategies. You can always implement a classical strategy using by just choosing corresponding, maybe like product state, product state, states, product states, and then making decisions, making observations, and then measurements based on your local F1, F2 kind of functions. So you can just do that. So therefore, Q star is at least C star, and then Q star minus C star is greater than or equal to 0. Okay, so I'll go on and talk about the very specific high-frequency trading case study that we did. So in the high-frequency trading scenario, I will first want to emphasize that this is a toy model. So this is a simplified scenario. Of course, in real-world applications, you have to look at historical data, you have to look at fidelities of different measurements or quantum operations, and to take into account all the different details of your setup to actually conclude that the quantum advantage is possible. Here we made some assumptions and simplifications to just make it clear, conceptually clear, that this is actually possible to get a quantum advantage in real-world HFT settings. So the setup is the following. We first have a trader. We'll call him Joel. He has co-located servers. So basically, those are servers that are physically located at each different exchange. So he has a co-located server in NYSE. He has a co-located server in NASDAQ. And then each server, they are issuing what they call in HFT ask or bid orders. So ask is a sell order and bid is a buy order. And then we're assuming that they're doing this for two different stocks, stock X and stock Y, which are two different exchanges. So stock X is at NYSE and stock Y is at NASDAQ. And what Joel is trying to do with his strategy is he wants to perform some kind of portfolio optimization to reduce his risk. So he doesn't want to let his portfolio value vary too much with the market. So this is what is known in the field as hedging. And you can, as I mentioned before, this high frequency trading setup the trading decisions are made at such high speeds, and the two exchanges are far away from each other, that these two servers don't have time to communicate. They can't tell. So for example, NYSE does not know what is going on at NASDAQ when they make their trading decision, and vice versa. NASDAQ does not know what's going on at NYSE when they make their trading decision. But somehow, in the setup that we're about to describe, they have to do some kind of coordination task to kind of optimize their portfolio to minimize the risk. Okay, so if the setup, we actually show that the CHSH inequality, the most famous inequality, Bell inequality, actually can appear in a real high-frequency trading scenario. So let's first assume by default that the price movements of stock X and stock Y are positively correlated. So if one goes up, and the other goes up, and if one goes down, the other goes down. So you can imagine an example, for example, Pepsi and Coca-Cola. These are two products that are very similar. You would expect their stocks to go up and down around together. So in this case, if the two stocks are positively correlated, then you would imagine that that draw should make opposite decisions at the two servers, like one buy and one sell, or one sell and one buy, make opposite decisions in order to hedge. So that is the assumption there. And then we also make the assumption that the servers also, they check for indicators. They locally look at, NYSE server looks at some NYSE data, and NASDAQ server looks at some NASDAQ data for an indicator that now these two stocks, X and Y, are now negatively correlated. They're no longer positively correlated, but they now are negatively correlated. In real life, this could translate to a situation where Pepsi and Coca-Cola are now companies that are at competition. So it's more important that these are competing firms than that they are similar products. In that case, those two stocks will now be negatively correlated. So you can imagine, okay, now they're negatively correlated, then now we should do the opposite thing, which is basically draw and should make the same decisions at the two servers to hedge. So each server buys and buys, or they both sell and sell. That also leads to hedging in the case that the two stocks are negatively correlated. So this is actually very similar to CHSH. So let's say, for example, if we require that both servers have to see this indicator of negative correlation in order for these two stocks to be now negatively correlated, the utility array, or the utility matrix, is now basically the same as CHSH. So remember, CHSH is kind of the Bell inequality, where you are now making same decisions or opposite decisions given your inputs. I'll go into that in a bit. So here, I'm drawing the utility array here. So here, the different letters, A is for ask. Ask is a sell order, and B is for bid. B is a buy order. And then I is an indicator. You actually see an indicator of negative correlation. And N, it means that you do not see an indicator of negative correlation, or in other words, these two stocks are positively correlated. So therefore, we have the assumption that we have to both see this indicator for the correlation to change signs. So that means in these three possible scenarios, remember the row indices are observations. So if both servers do not see an indicator, which means the two stocks are positively correlated, in that case, in order to hedge, these two servers should be making opposite decisions. So one ask, one bid, and one bid, one ask. And then we'll say that you get 1 point for doing the correct thing. And you get 0 points if you do the wrong thing. If you both ask or both bid under this condition, this observation, then you did the wrong thing. So you get 0 points. These numbers are kind of arbitrary. In real life, you have to fill this in with other numbers, but you can kind of get the idea from this toy example. So for these other two observations sets, and I, so one sees the indicator and one does not see the indicator, or IN, we assume that we made the assumption here that they have to both see the indicator. So in these two other scenarios, it's also the case that two stocks are positively correlated. In that case, you also want to make the opposite decisions. So you get the same kind of rows, 0, 1, 1, 0, and 0, 1, 1, 0 for these other two examples. In the last possible set of observations, you both see the indicator of negative correlation. then these two stocks are really now negatively correlated. In that case, in order to hedge, you need to make the same decision. So both ask or both bid. So now the row for this observation set is 1001. Okay, so it's basically it comes down to the case where in these three possible scenarios, you want the two servers to make opposite decisions, and in the last possible scenario, you want the two servers to make the same decision. So I'll just remind everyone here that this is the CHSH inequality, or this is the quantity that's less than or equal to 2. In here, you see A0, B0, A0, B1, A1, B0. These are the three possible settings or measurement settings, like 0, 0, 0, 1, and 1, 0. In these three settings, you want A and B to have the same value, like they can take values +1 or -1. You want them to be positive. You want them to be as big as possible. So you want them to be both +1 or both -1, so that these three quantities are large. And then the last one, A1, B1, so measurement setting 1, 1, you want these two observables to be opposite, so +1 or -1 or -1 +1. So in this CHSH inequality, in three scenarios, you want the two parties to make the same decisions. And in the last scenario, you want the two parties to make opposite decisions. So you can see that's actually the opposite condition of what we have in the utility matrix shown here. But by symmetry, you can just argue that this is exactly the same thing. It's the same quantum advantage, same kind of quantum strategy can get you that quantum advantage. All these things are the same by symmetry. Okay, grab a bit of water. Okay, so this is the most simplified kind of setup. You can imagine a more general case. For example, if you see one indicator and one does not see an indicator, and Ni or In, in that case, it might not be very clear if it's positive or negatively correlated. In that case, we add a parameter beta that's between 0 and 1. That kind of tells you if we should prefer same decision or opposite decisions. So for example, if beta is large, it means that you would prefer in these two scenarios for these two servers to make the same decision. If beta is small, you're preferring them to make opposite decisions. The last parameter we also want to add here is this probability that you do see this negative correlation indicator. So I occurs, these two different indicators, one at NYSE, one at NASDAQ, we assume that they occur with some probability P. So they're independent, Bernoulli distributed with parameter P. So this actually defines what we call the hedging problem, which is basically this utility matrix with a Bernoulli P input distribution. So these two parameters, P and beta, which are both between 0 and 1. And then you can actually do some very simple numerical simulations of what is the quantum advantage that you can get for different combinations of P and beta. So here, the picture here on the right here is the quantum advantage. It's basically the white squares are 0, so there's no quantum advantage for those. But you can see all these colored squares, yellow is the highest quantum advantage that you can get. That is possible for all these different P and beta values. So what I'm trying to send as a message here is that, for example, while for the CHSH inequality or the very simple utility matrix I showed in the last slide corresponds to P equals to 0.5. So each party sees the indicator of 0.5 probability, and the beta is equal to 0. So this is the highest possible quantum advantage that you can get. But there's also quantum advantages possible for different possible P and beta values other than just 0.5 and 0. So what this would correspond to in reality is that people will do some market research. They look at some correlated stocks like Pepsi and Coca-Cola, and they figure out what is P, what is beta, and then they put that into their utility matrix, and then they can compute using numerical simulations or numerical computations what is the best quantum strategy you can do to get the biggest possible quantum advantage. And then you can just do that for different pairs of stocks, and then you can just implement that physically using quantum communication platform. We'll get into that later. Okay, so now talk about the physical implementation. How do you actually implement these quantum telepathy schemes? So we will classify these different possible physical implementations into two types. For type 1 implementation, what is known as a direct photonic connection, is very simple. You now have, this is what you would expect a Bell inequality violation experiment to look like. So we'll just keep using this HFT scenario as an example. So at NYSE, let's say we have a server rack that we rent out at NYSE, and then we put a measurement device, like a single photon detector in the server rack. Okay, so some of the things I'm saying may not fit into a server rack, but let's say in the future or near future, we can make everything integrated so that we have this kind of quantum optical setup that fits into a server rack. So we put the server rack into server rack at NYSE, and we put one setup at a server rack in NASDAQ, and then the server rack will get input from their local observations. So at the NYSE server rack, single photon detector will get information. Do you see the negative correlation indicator, or you do not see the negative correlation indicator? And similarly at NASDAQ. And then in between NYSE and NASDAQ, there's entanglement generation source. So it's basically what is used pretty often in the field is like a polarized entangled polarization entangled photons. So basically a laser with a nonlinear crystal, and then the two pairs of photons come out. One goes to NYSE, one goes to NASDAQ. Each goes like 28 kilometers. Maybe we use it with fiber, which is the most convenient medium to use right now. And the two photons, one goes to NYSE, one goes to NASDAQ. And depending on whether or not they see a negative correlation indicator or not, they have different measurement settings. So like, for example, a polarizer before the SPD that you change the angle of, depending on whether or not you see the indicator. And then you do detection. Do you see the photon or do you not see the photon? And then depending on that, you do an ask or a bid. That's basically what a type 1 implementation will look like. So the key specs of a type 1 implementation, one is the entangled photon generation rate. So how fast can NYSE and NASDAQ get these entangled photons? It's like how long do you have to wait in expectation for entangled photon to come? That is one thing that is important. If it's not fast enough, then you're trying to do a high frequency trading scenario strategy. Your entangled photon is not coming fast enough. That's not good enough. So another thing that you want to consider is photon loss. So what is annoying is that these two exchanges are pretty far from each other. So over fiber, the loss is pretty large. So there's a good chance that your entangled photon that starts off in the middle at your entanglement generation source, this photon here, for example, will traverse this 28 kilometers, almost get there, and then just disappear. It gets absorbed by the medium. In that case, you cannot implement your quantum strategy. So actually, this photon loss is actually a big problem for type 1 implementations. So one, as I mentioned before, sometimes because of photon loss, you do not even have entanglement available to do your quantum strategy. But what is more even serious is that you might get your photon, you might get lucky, your photon gets to you at NYSE, but at NYSE, you do not know if the party at the server at NASDAQ received their photon. So if you wait for them to tell you if they receive their photon or not, then you have to communicate. That doesn't work. So in this case, you only have probabilistic control of the strategy that you're implementing. So sometimes you're doing a quantum strategy, sometimes you're doing a classical strategy, sometimes you're just doing some kind of mix of quantum classical strategies. You don't know what you're doing. And this actually leads, in the worst case, to a loss of quantum advantage. So if you do this kind of probabilistic mixture of strategies, you get a probabilistic mixture of utilities, and then that could be lower than the highest possible classical utility. In that case, you lose your quantum advantage. And then if you are familiar with the Bell inequality violation literature, this is also known as the detection loophole in the literature. And one thing you can get around is, okay, let's just fiber maybe is a high loss kind of medium for quantum optical setups. We can also figure out if there's lower loss mediums. And so one of the things that my co-author Liang worked on is something called a vacuum beam guide. So if you guys know LIGO, the gravitational wave detector, they have this long L-shaped arm, and each arm is basically a vacuum tube. And so that it can have this kind of optical interferometer setup with very low loss. And then their idea is to basically turn this vacuum tube into a quantum channel. So instead of like a huge vacuum tube, like meters wide, you make it like centimeters, and you're like centimeters wide, and you just make it really, really long. And then because it's basically a vacuum in there, it's very low loss. You can transmit quantum information across continents using this vacuum beam guide. It's still it's very interesting idea, but still something that needs to be implemented experimentally. And then another thing is that we can do that is commercially or even like experimentally available right now is that you can use quantum memories with what is called a heralded entanglement scheme. So what does this look like in a picture is that now at two different exchanges, you have a more like upgraded setup. Instead of just a measurement device and SPD, you now have a quantum memory. So for example, it could be NV center, nitrogen vacancy center. And so what they're doing here is they have this kind of setup where you have this NV center here and NV center here. You can do this kind of heralded entanglement scheme, which is basically kind of entanglement swapping, where you have entangled, you have a NV center and it emits a photon that is entangled with the NV center. And similarly here at NISE, you have an NV center that emits a photon that's entangled with the NV center. And these two photons that are originally entangled with the NV centers that they came from, they travel to a central station, the heralding station, where they do a Bell measurement. And then you can do the relevant mathematics, kind of entanglement swapping kind of basics, but this will lead to entanglement between the two NV centers themselves. So in this case, the nice thing about this kind of setup is that you have a complete control of the strategy that you're implementing via this heralding kind of setup. So the central station, they can tell, oh, have the two photons successfully arrived? Have I done my Bell measurement correctly? If all these things are true, then you can do the mathematics. These two NV centers are now entangled, and then they tell each other. They tell the two servers. So this classical signal comes out and tells the two servers that your NV centers are now successfully entangled. So in this case, you don't have to worry about this problem that, oh, I received my photon, but I'm not sure if the other party received their photon. You now know that these two things are now entangled because the heralding station has told you that. So now you can completely tell what you're doing, that you're actually implementing a quantum strategy. So the key specs of a type 2 implementation is, again, this effective entanglement generation rate. How fast can these NV centers be entangled? And the last other thing is like fidelity of quantum operations. You need to make all these operations of entanglement swapping, linear Bell measurement. These things will add up and cause errors in your quantum device. But we'll talk a bit more about the effective entanglement generation rate. So here there's a picture again of the type 2 implementation. You can actually do a back of the envelope computation of what the the entanglement generation rate is. So first, let's say the two servers, they're separated by a distance d. And then we also define this entanglement attempt time. How long does it take for them to try to achieve entanglement? So this is basically for large distances, for large d, this is mostly dominated by travel times. So of course, there's times taken to do the measurement, to do the entanglement kind of swapping between the NV center and the photon. But for large distances, TA is dominated by the travel time. So the entangled photon, here, for example, coming from the right side is going to take some time to get to the heralding station. And there's also the heralding signal return time. So after they do the measurement, the Bell measurement, they have to tell the two servers that the two NV centers are now entangled or they're not entangled. And that takes time as well. And these two times added together is basically a round trip speed of light around. And that gives you the entanglement attempt time, TA. And then the next thing is the probability of successful entanglement, PS. So PS is there's mostly two components to this. One is that the photons successfully make it. So here, you only care about the photon that's traveling to the heralded entanglements generation center. So this is because this is like a single NV center and a single photon comes out. And so there's some chance that it gets lost in the fiber connection. There's also, for this part, the classical signal part, you can just make that as big as possible. It's a classical signal. You can just amplify it. So you don't have to care about losing your signal there. But you have to care about the single photon that's carrying your entanglement being lost. And that contributes to PS. And the second one is the linear Bell measurement success probability. So like this, you can prove this paper from 2001 show that with linear optical instruments, you can only successfully implement a Bell measurement with probability 1/2. So that something like that would also contribute to PS. And then there's also the multiplexing factor. So you can imagine, okay, if this setup makes entanglement every time scale time t, you can just divide t by m, multiply the multiplexing factor m by just copying this setup, just m copies of the setup here, and that leads to a faster entanglement generation rate. So you can do a order of magnitude generation rate calculation. RE is equal to m times PS over TA. So this is like in units hertz. So this is basically how fast you can make entanglement with these two distances. So one thing I want to emphasize here is that you can do this back of envelope computation, and you can compare it to what the time scales that HFT occurs at, and you might see that it's actually too slow for HFT. But one thing that we asked HFT practitioners, and they confirmed with us, is that even though that these HFT kind of trading decisions happen at microsecond or very like sub-microsecond timescales, individual trading decisions, like different trading decisions, are pretty sparse. Like they make these decisions very quickly, but they do not make these very fast decisions all the time. In fact, these trade orders, the time between orders could be seconds or even hours. So while you make the decision very quickly, microseconds, the next decision that you need to make might be a few seconds later or hours later. So if you do a back of the envelope computation for NYSE and NASDAQ for 56 kilometers, you can show that even with one copy of memory, equals to 1, the entanglement generation rate is around 250 hertz. So entanglement is available every 4 milliseconds for this setup. So the main takeaway here is that the current technology, what we can do right now, like NV center or trapped ion at 56 kilometers with a fiber optic connection, a linear Bell measurement set up in the middle, that can actually be enough for high frequency in the HFT scenario. Okay, and now I'll conclude with some points in the discussion. So I want to also mention that other than HFT, there are also other possible applications of quantum telepathy. So HFT is a very cool example. You can imagine, but like you might imagine that you want quantum telepathy applications for normal people. Most people don't engage in HFT. Even if they do trading, they don't do it at those kind of timescales. But you can imagine maybe there's applications for normal people as well. And one example is maybe, for example, distributed computing. A normal person might be trying to run something on the cloud, and then that goes to some kind of a data center. And then this goes to a problem of distributed computing. So a data center is around a distance of 100 meters, for example, in length scale from one end to the other. And then with that 100 meters kind of distance computations are like around 0.1 milliseconds apart are actually already space-like separated. So it's not possible to communicate if you're making computations faster than 0.1 microseconds. So you can imagine for this kind of generation rate that you need, like 0.1 microseconds, you need multi-megahertz generation rates. And that's actually already possible with current technologies. So you can just get a laser with a nonlinear crystal, and that actually produces entangled photon pairs with multi-megahertz generation rates with a feasible laser power. And then at a distance scales of 100 meters, that's not very far at all. You can just use optical fiber to achieve efficiency of like 0.998. So it's actually already very good. So I would actually argue that for in terms of the distances involved and the generation rates that you need, distributed computing is actually the most ideal parameter regime. HFT is kind of a bit too far, like 50 kilometers. Maybe if you want to go like Chicago to New York, it's like 1,000 kilometers. Those kind of distances, it's kind of hard to distribute entanglement to violate Bell inequalities. For distributed computing, that might be a lot easier. Another thing is computer architecture. So instead of two computers that are at two different ends of a data center, you can just imagine one computer, like CPUs and memories inside, and these are also doing operations at very high speeds. And you can imagine that a TC problem might be entailed. So for computer architecture, you might imagine like distances between CPUs or memories that might be on the order of a centimeter. So in that case, you might imagine, okay, this centimeter is like 0.01 nanoseconds, like 10 to the minus 11 seconds. If you want, there's not really operations that are going on at those fast time scales. But one thing I want to mention here is that in computer architecture, these kind of CPU integrated circuits, the latencies between CPUs or these different devices are not dominated by a speed of light delay, but actually the RC, the resistive capacitive time delays interconnects. If you remember from some circuit class, that these RC time delay exponential curves, those are kind of the time scales that are involved when you talk about latencies in these kind of integrated circuits. So those can be a lot, the latency can be a lot longer than 0.01 nanoseconds. And then you can imagine, also know from just looking up these kinds of numbers that the memory latency of these devices can be like 10 nanoseconds or like 100 microseconds. So this is actually these latencies are actually relevant and might be too long for the timescales involved in computer architecture operations. And if you want to make generation rates of like gigahertz or faster, then you need to do something more than what we are doing with current technologies. There are some progress towards that. As an example is this 2020 paper here that we're able to achieve gigahertz generation rates. And then in this case, if you're looking at these integrated circuits, you can't use optical fiber anymore. You use something that can be integrated. So like an optical waveguide can achieve, for example, a 0.955 efficiency. So efficiency here means the probability of not 1 minus probability of loss. The probability of loss here is like 0.045. So this is kind of the efficiencies that you can achieve here. And I also want to mention here a computer architecture example that I thought of. First of all, I want to give a disclaimer. This is a hypothetical computing machine. I told this to my CS friend, and he said this doesn't really make sense. But you can imagine a universe where this kind of computing machine exists, and it kind of gives you a flavor of how Bell inequalities can appear in computer architecture setups. So the example is the following. We have two CPUs that are reading from memory at gigahertz clock speeds. And so first of all, we're assuming they're just doing reading, they're not writing, they're just reading from memory. And the first assumption that we make is that there's two copies of the memory. And then the second assumption is that it's preferable to read from the same memory. So maybe it's actually better to show the picture here first. So there's CPU A here, CPU A and CPU B, and they're making read operations from memory 1 or memory 2. And we're assuming that memory 1 and memory 2 are copies. So maybe, for example, these two memories, this memory is very important. You want to make a copy, so you put two copies of memory, and they're just making read operations. Second assumption is that for the most part, you want these two CPUs to be reading from the same memory. So an example that a possible reason I thought of is maybe like energy conservation. You want to read the same memory, so you just turn one memory on at the same time. This maybe doesn't make sense of current technologies, but this is a hypothetical computing machine that for which it could be the case. And then the second thing that we want to mention is that these two CPUs are reading from memories at different addresses. So for example, CPU A is reading from addresses 1 and 2, and CPU B is reading from addresses 2 and 3. And then I picked these kind of numbers so that we can actually get the CH-SH inequality. So for example, if we consider the pairs of addresses that the two CPUs are trying to read from, then for example, if CPU A is trying to read from address 1 and CPU B is trying to read from address 2, then by assumption 2 is preferable for them to read from the same memory. So you want the desired read pattern for the two CPUs to be reading the same memory. And for 1 and 3, same reason, you want these two CPUs to be reading from the same memory. And then for 2 and 3, CPU A is reading from address 2, CPU B is reading from address 3. You also, again, you want them to be reading from the same memory. And only the last possible scenario where they both are trying to read from address 2, you now want them to be reading from different memories, because now they're going to collide. If they read the same memory, same address, they might lead to a collision. In that case, you want the two CPUs to read from different memories. It doesn't matter which memory they choose, it just has to be a different memory. And this is basically the CHSH inequality all over again. The three situations, you want these two CPUs to be making the same kind of behaviors, same decisions. And on the last situation, you want them to make the different decisions. Okay, so the basic conclusion here is if you have this hypothetical computing machine where this assumption 1 and assumption 2 holds, and you have this setup, then it actually leads to a CHSH inequality. You can give CPU A and CPU B two halves of entangled state, let them make measurements, and then they'll lead to this kind of read pattern that you want for these different address pair possibilities. Okay, and last thing I wanted to mention is possible future research directions. So the first thing that is most important here is to do a detailed, full detailed engineering analysis of a TC problem in an industrial setting. So first of all, the utility array is not just very simple 0110 or 1001. It's all based on real data. It's all these different numbers that are based on, for example, in HFT, historical market data. 2 is you do a whole physical implementation and you do an in-depth physics simulations to figure out how fast can entanglement be generated, what is the fidelities of different operations, what is the photon loss, and you must all add up all these details together. And then you also, of course, you want to figure out, okay, how much money or how much risk can you reduce with this kind of strategy, and is it actually worth putting investment into this physical implementation? And it's actually very exciting for me because I think this is actually leads to some very application-centered research. So this actually tells you this is the application that we want. We can figure out the kind of theoretical and experimental questions that we need to address to make this application happen in real life. So for example, theoretical questions that you might want to think of is trying to figure out efficient classical algorithms to find the optimal telepathy schemes or quantum strategies for more general TC problems. So if the most general TC problems is actually very hard, you can prove hardness results for these kinds of scenario for most general problems. But you can imagine maybe some special class of problems that we're interested in. We want to figure out efficient algorithms to compute the best quantum strategy for those. And another question is multi-round TC problems. So you can imagine like HFT, like you're not just solving one TC problem. It might be a TC problem one moment, a different TC problem in a different moment. It might be a time dependence of the utility matrix or the input distributions. In those kinds of scenarios, what is the best thing you can do to pre-share entanglement, to do the measurements accordingly, to get the best possible quantum value. And then for experimental questions, you can imagine, for example, HFT, this needs to fit into a server rack. You need to do some system integration to make everything smaller than what people are doing in labs right now. And then for like type 1 implementations, one question is how do you conveniently distribute entanglement with general quantum states? So not just a maximally entangled state or a Bell state. You want to figure out more general quantum states. How do you distribute those entanglements with an entangled photon pair? And type 2 is, for example, if you want to how to do implementations of multiple memories, if you want to increase your entanglement generation rate, you want to do this multiplexing factor M, you need to have different memories together in one device. And that is something that is still a direction being pursued in the experimental community. And that is it. Thank you.
Thanks for Professor Ding for such interesting lecture. And we're now coming to the Q&A time. Any questions from audience? You can feel free to unmute yourself or you can directly type in the chat box. Yeah, actually, I've seen there's some message in the chat box
Mm-hmm.
from I believe one of them is already live, but he's asking what is the O and D.
Oh, okay. So this is probably the slide here. So I'm talking about different observations that different parties can make, and I making the simplifying assumption that there's only two possible observations. So each party can see O or O prime. Those are observations they can see. So in the HFT
Yeah.
scenario, basically, do you see the indicator or you do not see the indicator? That's basically what the O and O prime correspond to. And D prime is for in the HFT scenario, do you buy or do you sell your stock? So two possible decisions that your two servers can do.
Okay. Hope he can get this answer based on the recording.
Yes.
Yeah. Another question is from Nathan Patel. What's the negatively correlation means?
Okay.
Thanks.
This is the HFT scenario. Yeah, here. So positive correlation, it just means that stock X and stock Y, they move together. So one goes up, other goes up, one goes down, other goes down. And then negative correlation, excuse me, negative correlation is when they are doing opposite things. So one goes up, one goes down, or one goes down and one goes up. That's what negatively correlation means. Negative correlation means.
Okay. So Nathan, is this answer your question? Okay. I think it's good. And I do have like a personal interest in the computer architecture part. If there's no other questions, any questions, any other questions from audience?
Yep. Uh,
Okay.
Okay.
yep. Thanks, Professor Dean, for a wonderful lecture. So I've noticed that you have mentioned the distance D in multiple scenario, maybe like the distributed computing and the computer architecture, right? So, but I
Mhm.
didn't see like any other formulas mention the distance D. So I just want to ask if the either say the or the system performance or even the quantum advantage will be affected by the distance or not?
Yeah, so here I'm talking about different other applications like distributed computing or computer architecture. I'm talking about distances here because the distance is very important. One, it determines how long is the speed of light latency between the two parties. So like 100 meters, like 0.1 microseconds or 0.3 microseconds. And then like 1 centimeter is like 0.03 nanoseconds. So those things tell you how long is the speed of light latency. And then that tells you you have to be doing things faster than that latency for there to be no communication enforced by relativity. So that's one thing about distances that is important. The second thing is that these distances tell you, is it possible with current technologies to distribute entanglement across these distances? So 100 meters, 1 centimeter, that's okay. 50 kilometers, that's okay. But like hundreds of kilometers, thousands of kilometers, that's not really feasible right now with current quantum optical technologies. Does that answer your question?
Yeah, perfect. I see. So it's more like a constraints about the system, how the system should operate. It's not about either say the efficiency, performance, or something like that.
Yeah, it basically tells you what scenario can you get this kind of no communication condition, and it tells you how hard is it to distribute entanglement across that distance.
All right, I see. Thanks. Thanks. And I think I'm done with my question, Professor Liang.
Okay. Yeah, I am also interested in the computer architecture example, that part for the memory. I'm curious, like I believe like here the memory is indicated like classical memory, right? It's not for those like QRAM, QROM stuffs.
All classical.
Oh wait, all possible, all classical.
All classical.
I see. Yeah, I just wondering if it's possible to probably cross-study this part with the QRAM concepts.
Mm-hmm. In
Yeah.
QRAM, you also make these really fast operations and you're not allowed to communicate?
Yeah.
Oh, okay. I wasn't aware of that. What are the distances and like time scales involved? Like how far apart, or is it like two different QRAMs or like two parts of the same QRAM? Or what does the setup look like?
Yeah, I'm thinking about like two parts of the same QRAM, since like
Mhm.
I actually never consider of a situation of like two different QRAM. So I'm just thinking about the like traditional QRAM, this kind of like a structure of the QRAM, and if we can do this theorem to the like two different parts of the QRAM, if it's possible to make the communication faster. Yeah, but it's just a interesting guess, I believe.
Okay. What kind of architecture are you considering? Like superconducting qubits or
Yes, we're connecting qubits.
superconducting qubits? Okay, yeah, those are fast. Those are pretty fast. So it is possible that you can get something like this. Is there like a setup that looks like this in a QRAM scenario?
There's actually no QPU, but I believe this like similar. So QRAM is basically a quantum circuit. We're currently using a group of quantum gates to represent a QRAM, and I believe that there's several qubits indicate the position. I mean the data, and there's several qubits indicate the address. So I believe like if we do some like high level abstraction to representing the structure, is kind of like similar to this one.
Mm-hmm.
Yeah.
Okay.
So
That'll be very interesting. Yeah, please let me know. Maybe we can talk offline. I'd like to know what the details of that setup look like and see if we can
sure,
map quality. Yeah.
yeah.
But I do want to mention that the examples I give in my talk are all classical, because in that case, it's very clear what the objective is. Like people have been doing this in the classical community all the time, like high frequency trading. They're trying to make money, reduce risk. In this computer architecture community, they're trying to like make operations faster, increase throughput, reduce collisions, things like that. So very clear what the goals are. And all I'm trying to show is that with quantum entanglement, you can do that same goal better. So in that case, it's very clear what you're trying to achieve and what
I
quantum
see.
advantage in that case. Yeah.
I see. Yeah, but it could be applied to a lot of like real world applications. Like I believe like recently people are investigating on like quantum computing for the drug development, the clinical trial, and there's like set selection and some like communication between local hospitals. Yeah, those kind of stuffs, I believe like those theorem could be really useful. Yeah,
Okay.
thanks again for Professor Ding's great talk. And if there's no more questions, we'll end up there today, and hope to see you guys next week. Yeah, thanks.
All right. Thank you.
Have a good day. Bye bye. Oh, have a good night, actually.
Yeah. Thank you. Bye.
Bye bye.